So we have kind of nice results. It's not as much as I would have liked to. It's not, it's not, but it's nice. Thanks.
Yeah.
I answer your message shortly. Okay.
Yeah, maybe I should invite you for another talk next time. Yeah. I really insist that. Yeah.
Sorry, I was kind of confused today, but long day yesterday, long weeks. Okay, so without further ado, it's my pleasure to introduce the next speaker, which is Ye He from the Chinese Academy of Sciences, who will speak on the geometry of convergence and analysis for low-ranked partially orthogonal tensors approximation problem. So please.
Okay. Thank you. Thank you very much for the introduction, Professor Emil Soken. Yeah, so first I like to, let me turn off the video because I'm afraid that my internet speed is not good enough to show my face.
Yeah, I know how, of course.
Yeah, okay. Yeah, so first I like to thank the organizers for the kind invitation. It's my great pleasure to give a talk at this conference. Yeah, the title of my talk is the geometry of the convergence analysis for low-rank partially orthogonal tensor approximation problem. So this is basically a combination of some like geometric tools from mathematics to do some convergence analysis for some algorithms regarding the tensor approximation problem. So this is based on a joint work with Chen-Long Hu. So let me first tell you about the outline of this talk, because I'm not sure how many audience here are familiar with the notions of tensors or hypermatrices. So I'm gonna first give you some brief introduction to tensors for non-experts. So, and after that, I'm gonna tell you what kind of problem we are interested in. Basically, I'll explain what is the low rank partially orthogonal tensor approximation problem and why we need to, we want to think about it. And after that, I'm gonna tell you what we have as our main results regarding this approximation problem. And the fourth part, which is the last part of this talk, will be more mathematical. I'm gonna tell you how geometry can be used to do the convergence analysis of an algorithm. Okay, so that's the plan for this talk. So first, let's look at the brief introduction to tensors. So basically, if you are working with data, then you can just think tensors as multi-dimensional data. Okay, so here I just steal a picture online that basically explains how people in all areas how they think about say vector matrix or higher order tensors. So basically for people who are working with data, you can just think of vector as array of number, right? It's just a line of number, and a matrix, that's just a square of numbers. And for a 3 tensor, it's just a cube of numbers. And then you have higher order, say 4 tensor, then it's just some array of numbers indexed by 4 indices, right? So this is just a tensor for people who are working with data. But of course, for people in physics or mathematics, there are some other interpretation of tensors. But for now, let's just forget about that. Okay. So here is just a list of examples to show you what is the difference between a tensor, a matrix, and a vector. So vector is just say a 2-dimensional vector, then it's just 2 numbers, and a matrix that we are familiar with matrices, right? So it's just a 2x2 matrix in this case. And for a tensor, you can have higher order tensors. So it's just in this example, it's just 8 numbers indexed by 3 indices, x, I, j, k, right? So you can, of course, you can regard this tensor as a stack of 2 matrices, right? So in this example, you can just sort those numbers indexed by, say, the first index is 2, so you get a 2x2 matrix. And then you similarly, you have another 2x2 matrix x1 and then x2. So you have a 2x2 matrix in this case. But soon we will see that tensors are very different from matrices. Let me show you why they are different. Well, first let's look at a very important notion for tensors or for matrix. So for matrix rank, we are familiar with that. Matrix rank is used to describe how complicated your matrix is. And similarly, you can define a tensor rank, which describes how complicated your tensor is or your data is. So for a rank 1 matrix, we can define this matrix to be a matrix A, whose entries can be written as, say, xi times yj. And if you use the tensor product notion, then this A is just a tensor product of 2 n-dimensional vector. So that's rank 1 matrix. And for a given, say, 2 by 2 matrix, you can always decompose this matrix as a sum of several rank 1 matrices. And basically, the rank of a matrix is defined to be the minimum number R, such that your matrix is a sum of R rank 1 matrices. So that's the well, maybe it's not the standard way to define the rank of a matrix, but that's equivalent to what we know about the rank, which is defined in terms of minors. Okay, so similarly for a tensor, we have a similar notion of rank. But first, let me tell you what is the rank 1 tensor. Similar to what we have done for matrices, you can define a rank 1 tensor as a tensor whose entries xijk is defined by xi times yj times zk. So in that case, you can simply write your rank 1 tensor as a tensor product of 3, say, n-dimensional vector. Okay, so that's a rank 1 tensor. Now, here I give you an example X. So here I just write this as a 2 by 4 matrix, but really you should think this tensor as 8 numbers indexed by 3 indices. Okay, so it becomes a 2 by 2 by 2 tensor. Okay, so if you follow the definition of a rank of a tensor, meaning it's a minimum number R, such that your tensor can be written as R as a sum of R rank 1 tensors, then you can see that the displayed tensor here, this particular tensor has rank 3. You can try to write this down, and it's very easy to verify that. Okay, so that's how we define the tensor rank and how it is related to the matrix rank we are familiar with. Okay, so that's the tensor rank. And as you can see, that's a tensor rank and the matrix rank, they are closely related. So you may think that maybe I can just treat the tensor rank as the matrix rank in some way. So we know how to deal with matrix rank. Right? It's computationally, it's very simple to do that. But for tensors, we will see soon that they are totally different. So again, let's take the same example. If you write this tensor as in terms of a tensor product notion, then it looks like this, where E1, E2, F1, F2, G1, G2 are respectively a basis for R2. Okay, so there's a technique for tensors, which is called unfolding or flattening in different literature. So you can always translate a tensor into a matrix, just like what I did here. If I give you a 2 by 2 by 2 tensor, that's my curly X here, then you can always write this as a 2 by 4 matrix. So you can see that the matrix representation, they are the same, but the way you index their entries are different. So recall that if you have a 2 by 2 by 2 tensor, then you have to index its entries by 3 indices, right? That's what we have seen before. But if you regard this as a 2 by 4 matrix, then you just need 2 indices to index its entries. Okay, so they have the same entry, but the way you index these entries are different. That's the main difference between tensor and matrix. Okay, and since you have different ways to index your entries, then you have different ways to define ranks. And actually, we can see that if you regard this curly X as a tensor, as a 2 by 2 by 2 tensor, we can show that the rank of this tensor is actually 3. But if you regard the same array of numbers as a matrix, as a 2x4 matrix, it's easy to verify that this 2x4 matrix has rank 2. Okay, so you can see that the same array of numbers has tensor rank 3, but it has matrix rank 2. So the tensor rank and the matrix rank, they are different. Okay, and moreover, you can always find a sequence of 2x2x2 tensors such that each one element inside this sequence has rank 2, but when you take the limit, it's approaching to x. And you can see that I can use a sequence of rank 2 tensors to approach a rank 3 tensor. So if you think about the same thing for matrices, you cannot do that, right? If you have a rank R matrix, you cannot approach this matrix by a rank R-1 matrices. You can never do that. But for tensors, you can. Okay, so this is a very big difference between tensors and the matrices. And for me, I think this is the most important feature of tensors, and that makes the computation or approximation of tensors very hard. Yeah, so this is the main example, right? I have a sequence of tensors that are approaching my tensors, but each one of tensor in this sequence has rank 2, but the limit tensor has rank 3. While if you do the same thing for matrices, you can never do this. Okay. All right, so that's the introduction of tensor and tensor rank. Any question for that? Okay, if not, then I'm gonna proceed to the second part about the low rank partially orthogonal tensor approximation problem. So for that, so let's first take a quick review on low rank matrix approximation. I think people are all familiar with this part. So basically, if I give you a n by n matrix, that's say you can think this as some kind of data, and then a low rank approximation problem is just the following optimization problem, right? You are trying to find a low rank matrix B such that the distance between A and B is minimized. So that's the low rank approximation problem. Now this problem is very well understood because first of all, if you take the set of all n by n matrices whose rank is less than or equal to R, then this set is closed. It's algebraically closed. So you know that the solution must exist. That's first thing. So that means this question, this optimization problem is well posed. The solution exists. And secondly, by the Eckhart-Young theorem, you can always use the truncated SVD to find the best approximant for A. Right, you can just do the truncated SVD and then you get the optimizer. So you are guaranteed to have a fast algorithm for this problem. And also, if you this shows the global optimizer for the for this optimization problem. And moreover, you can by the definition of the truncated SVD, you can see that these factors x1 to xr are orthogonal, are all orthogonal to each other, and y1 to yr, they are orthogonal. Okay, so this is a very useful feature for low rank approximation. And moreover, if their singular values are all distinct, then you can guarantee to have a unique solution for that. Well, if this is the generic situation, right? So for a randomly given matrix A, you can always expect that it has distinct singular values. So once they are different, then the solution to the optimization problem is unique. That is guaranteed. So basically, this low rank matrix approximation has lots of good properties, like the solution exists, and you also can have a fast algorithm for that, and even you are guaranteed to have a unique solution. So that's very good. But in application, what if your data is higher dimensional? Meaning, what if your data is a tensor, right? So here I just take n by n by n tensor, for example. You can do the same thing for tensors of any order. Okay. So we can consider the same problem, right? I give you a data A, which is a tensor, then we're trying to find a low rank tensor B, so that the distance between A and B is minimized. Okay, so we are considering the similar problem. Now, for tensors, unfortunately, there are different notions of ranks. There's no unified way to define a rank. So the CP rank is just the rank we defined, say, several slides before. And if your tensor A has some special structure, you can define symmetric rank, or you can even use a simpler one, which is called the multilinear rank, and so on and so forth. You have many different versions of ranks for tensors. And for when you restrict these tensor ranks to matrices, then they all coincide. So that's why the matrix is always simpler than tensors. For tensors, you have different notions of ranks, but for matrices, basically just have one. Okay. Now let's consider this question first. So if you take the n by n tensor, n by n tensor whose rank is less than or equal to R, unfortunately, this set is not necessarily closed. So that means it's possibly true that you cannot find a best approximant for your problem. So that means the existence of your solution is not guaranteed. Secondly, we can see that a tensor is a multilinear array, but the linearity is not linearity. So you cannot expect that we can solve a problem related to tensor by just say numerical linear algebra. Actually, it is proved that if you want to do anything about tensors, then the complexity is NP hard. You cannot expect to have a fast algorithm for tensors. Say, a typical example is that if I give you a tensor and I ask you to find the rank of this tensor, then this will be NP hard. It's very hard to determine the rank of a tensor actually. And due to some kind of geometric property called the dimension defectivity, in general, the solution of this low rank approximation problem is not guaranteed to be unique. Meaning you can have, first of all, the solution may not exist. Even if it exists, you may find many of them. It's not unique. Okay. So that's the low rank tensor approximation. This is a direct generalization from matrix to tensors, right? If you look at this this formulation here, so you can ask the same question, but unfortunately we do not have good properties as for the matrix version. So the way we are trying to resolve these issues is to do something. We just either relax your optimization problem, or we restrict our optimization problem to some smaller domain. So in our case, where we are restricting the low rank approximation problem for tensors to some smaller domain. The advantage of this method is we are transforming something which is computationally hard to something that is easy. So we have now we are ready to introduce what is a low rank partially orthogonal tensor approximation, which is abbreviated as LRPOTA. So here's the question. I give you a data which is n by n tensor, and I pick a number S, which is in the set 1 to 3, either one of them. So my LRPOTA problem is just I'm trying to find a low rank tensor B. So we have the same constraint on the rank of this tensor, but so we have more structure. I require this tensor to be S partially orthogonal. So S partially orthogonal, I'll explain this in details later, but briefly speaking, this S partially orthogonal is just some orthogonality constraints on B. So I'm trying to find such a B such that the distance between A and B is minimized. So you can see that I'm just adding one more structure, which is the orthogonality structure on B, so that's I restrict the original low rank approximation problem to a smaller domain. So of course, if you have a tensor whose rank is less than or equal to R, then you can expect this B to have this decomposition by definition, right? So each one of them, X1 tensor, Y1 tensor, Z1, that's a rank 1. So since your rank is less than or equal to B, so you have to write this B as a sum of at most the R of these rank 1 tensors. That's a definition of rank, tensor rank. And by S partially orthogonality, that means you require that the first S factors of your decomposition to be orthogonal. So here I just show you what it means for different values of S. So for if you take S to be 1, then that means X1, X2 up to XR, this set of vectors, they are orthonormal to each other, okay? And when S is equal to 2, I require X1 through XR to be orthonormal to each other, and Y1 through YR to be orthonormal to each other. And similarly, when S is equal to 3, I require X1 through XR up to, say, Z1 through ZR. These three sets are respectively orthonormal. So from this setting, you can see that by choosing different S, you have different constraints on your factors. That's just the orthogonality constraints. So this is our low rank partially orthogonal tensor approximation. We are doing nothing but just imposing some orthogonality approximation on your target tensor. So if you recall what we have done for matrices, right? If you have a truncated SPD, then those factors are orthonormal automatically. And what we are doing here, we are trying to do the same thing for tensors. We're just requiring, say, partially orthogonality here. Okay, so that's our question. And yeah, so since we have if you look at this question here, our constraints, we require our B to be has rank less than or equal to R, and we also require it to be S partially orthogonal. So those are just some kind of abstract conditions. So actually you can do some parameterization of this question. So here is what we have. We can write B as a sum of rank 1 tensors, such that when, say, S is equal to 1, then I just require that Xj and Xk to be pairwise orthogonal, and Yj, Zj are unit length vectors. And also this sigma j, I can require this sigma j to, okay. Okay, so when S is equal to 2, we have the similar formulation, but this time we are requiring Xi's to be orthogonal to each other, and we also require Yj's to be orthogonal to each other. Okay, and similarly we have S3 and so on and so forth. Yeah, here I just take a order 3 tensor as an example, but you can do the same thing for higher order tensors depending on your actual question. Okay. So okay, now mathematically we have a low rank tensor approximation problem, and we don't know how to solve it, so we restrict our question to a smaller domain to have LRPOTA. But why we should care about such a question, right? So here I just list some of the applications that I can find. It's not a complete list. There are many other lists. There are many other applications that I didn't put in here. Basically, since tensors are always used to represent higher order data, so you can find these tensors appeared in many areas, and the orthogonality is some kind of mathematical notion for independence. So basically, you can find these orthogonal tensor approximation in many areas like latent variable models or signal processing or data mining or independent component analysis or even tensor network states. So you can find many applications in these areas. Okay, so yeah, that's the origin of this LRPOTA model. Now we have a optimization problem. So you may wonder how can we solve it, right? So again, if you want to find the exact solution for this question, as I said, this question itself is NP hard. You cannot expect any faster algorithm for this question to find the exact solution unless you believe P is equal to NP. But then you can have some approximation algorithm, right? It's like say naively you can just think about the say gradient descent, something like that. But since we have orthogonality here, so we have some other tricks to do that. There are some kind of methods like a Jacobi type or power methods, or even APD or IAPD. So in this talk, basically what I'm talking about is related to APD. So this IAPD is what we proposed and what we analyze. So basically, IAPD is just the improved version for APD. So the full name for APD is the alternating polar decomposition. So you can see that we are alternating factors, and then since we need to take care of the orthogonality, so we are doing the polar decomposition in some substep. So that's the where this name comes from. So by alternating, here's what I mean. So our objective function is something like this, right? We have a given data A, and we're trying to find some lower rank tensor with orthogonality constraints here. So what we're trying to do is we can fix two factors, say xj and yj, and we can optimize the third. That means that we can optimize with respect to zj, and then we're just alternating, right? So next step, we fix yj and zj, and then we optimize with respect to xj. Well, the advantage of this method is that once you fix two factors, the rest one will just be what we know, right? When you fix xj and yj, then the problem becomes the least square problem. So you know how to solve a least square problem. So in the literature, it's called well, there are two names for that. The first one is the block coordinate descent, but the other one is the alternating least square. I think the block coordinate descent is a more general name for such a method in the literature, but the alternating least square is only for people who are working with tensors. So I think this such a question are considered like maybe 10 years ago. At the beginning, people are just trying to find some algorithms for this question, for this problem. I think the most widely used algorithm is the so-called APD, the alternating polar decomposition algorithm. And until say maybe 2015, people are trying to consider the convergence property of this algorithm, but people have to add some add some conditions on this problem. Say they need to assume that in each iteration the iterates satisfy some conditions, so they can prove the global convergence and blah 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 blah, something like that. But these conditions are not easy to verify because the iterations is infinite progress, so you cannot check all the conditions for each of the iteration. That's not possible. So these conditions are not very practical, actually. And then in 2019, and also this year, our work shows that unconditionally our newly proposed algorithm is global convergence, and also we have a estimate for the rates. The reason that we can achieve such a convergence in the rate estimate is that we use tools borrowed from geometry, while people before who are working with this problem are mainly using the tools from the optimization theory. So that's the main difference. All right, so let's look at some special cases of LRPOTA. Basically, for different values of this S, we have different interesting problems. So let me take PSNR to be the set of n by n by n tensors, which is S partially orthogonal, whose rank is less than or equal to R. So this is the feasible domain of our optimization problem, right? Then you can see very easily that you have an interpolation of spaces from P3 to P1, but actually if you just take S to be 0, that means you are removing this S partially orthogonality here. So you just have one condition, that is the rank of B is less than or equal to R, so that you actually have P3 containing P2 and then P1 and then this P0. Now, for P3, we actually have the low rank orthogonal tensor approximation. So this is a very special case, right? You are requiring all the three factors to be orthogonal to each other respectively. Okay, so this is a very special case. And when you take P0, then you are removing the orthogonality constraints and you get back to the low rank tensor approximation. Of course, in our work, we do not consider P0, so that's why it's in parentheses. But you can regard our work as some kind of interpolation of this P0, right? If we just take S to be 1, then this is really the space inside P0, and we are just requiring that at least one factor of your decomposition has some orthogonality. When R is equal to 1, then we just get the rank 1 tensor approximation problem. This is a very, very well studied problem in tensor computation. So because this rank 1 tensor approximation is the simplest case for tensor approximation and tensor computation. Okay, you can find many papers on this rank 1 tensor approximation. Okay, so these are special cases of LRPOTA. All right, so now we know what is the so-called low rank partially orthogonal tensor approximation problem and why we want to study it. Now, first, let me just tell you what we have regarding this question. So first of all, we have this algorithm. So regarding this question, LRPOTA, we have the following algorithm, which we call the IAPD ALS. It's basically just a combination of several tricks. It's APD, that's alternating polar decomposition. That's the original algorithm that's already exists in the literature. And then we have the proximal correction and truncation. Those are just some sub-steps that we add to make sure that our convergence analysis can hold. And we can even prove that after finding many steps, those proximal correction and truncation will disappear. So basically, our algorithm is exactly the original APD algorithm after finalizing many iterations. And also we have ALS. So this ALS is the alternating least square method because for us, we're allowing this S to be smaller than 3, right? So when, say, for example, when S is equal to 1, you just require XJs to be orthogonal, but you do not have orthogonality for YJ and ZJ. So in that case, when you are dealing with YJ and ZJ factors, you do not have orthogonality constraints. So in that case, you cannot use the polar decomposition to do that. But instead, you need to use the alternating least square, the naive least square least square problem. You want to solve that. So here is the flow chart of our algorithm. Basically, we're just updating the, each time we just fix some, fix all the components except one, and then based on whether or not this component is required to be orthogonal, we choose to use either the polar decomposition or just the usual least square optimization to find the, to solve the sub-problem, and then we just continue and iterate. And this proximal correction and truncation are just some small steps that we insert in these steps. So basically, this is just still alternating methods to solve this problem. So that's the algorithm. Okay. So I think the most important part of our work is that we did a complete convergence analysis for this algorithm. So first of all, we can prove that the algorithm converges for any A. Okay, so this is not achieved by works before, and moreover, we can even estimate a sublinear convergence rate for every A with no additional assumption. And this rate is already better than general non-convex optimization problem. So for a general non-convex optimization problem, the best one can get is it's just the O1/k. That's a rate, but our rate is better than that. And for a generic A, we can even prove the linear convergence rate for a generic A. So here, this genericity is some notion in algebraic geometry, but if you don't know this genericity, you can think that if I randomly pick a tensor A, then the probability for our algorithm to be our linear convergence rate is the probability is 1. Okay, so that's what this genericity means. And there's another work in 2015 which constructs several examples to show that actually for different choices of A, any rate can occur. It can be sublinear and linear and superlinear. So our work shows that for almost all A, the algorithm is linear, has a linear convergence rate. Okay, and it is guaranteed to be at least sublinear. So for superlinear convergence, our algorithm, our result shows that it only holds for a very rare A. So if you are interested in this convergence analysis, you can see these two papers. The first one is about a very special case where all factors are required to be orthogonal. And the second one is for a more general case where you allow some of them to be orthogonal, but some of them are not allowed are not required to be orthogonal. Okay. So that's basically our results. Now we come to the mathematical part for this work. So basically, I tell you how the geometry is used to do this convergence analysis. So essentially, we're just first of all, we are just trying to relate the parameter space with the feasible sets of the question. So if you recall, what is our LRPOTA problem? That's just find a point inside this PSNR, the set, such that the distance between A and B is minimized. So this is something like the projection problem, right? If you have a set and you have a point outside the set, and you're trying to find the point on the set, so the distance is minimized. And for such a question, any first order algorithm, the best you can expect is to find a critical point for such a question, for such a problem. But when you try to solve this problem numerically, you have to do some parameterization, right? Because this PSNR, this set is some abstractly described set. You have to parameterize this set so that you can do some numerical algorithm, or you can do the you can do the experiments for that. So what we do is to parameterize the problem, and it turns out that the problem becomes a constraint optimization problem, right? Because here we have sigma j is a non-negative real number, and also xj is the first vectors are orthogonal to each other. So for such a problem, you can expect it to have a KKT point, right? You have before we have some kind of projection problem, so you can expect to have a critical point, and now you parameterize the problem, then you have a constraint optimization problem, so you can expect to have a KKT point. So what's the difference? The difference is that in the parameterized version, we have a parameter space, which is VRN cross BRN cross BRN cross RN. So let me tell you what are they. So first of all, this VRN is just the so-called Stifel manifold, which means it's an n by R matrix whose columns are orthogonal. Okay, so that's the definition of VRN. And BRN is just the product of bunch of spheres. So this is the n by R matrix whose columns are of unit length. So that's for Y and Z. Okay. Now, how the parameter space is related to our feasible sets, we just have this map, right? If you give me X, Y, Z, and sigma, so this sigma is just a sigma 1 through sigma R, corresponds to this the last component R here. If you give me such a data, then I can construct a tensor corresponding to this data. So that's my phi NR. So using this map, we can connect to the parameter space with the feasible sets of the original problem. Now, so if you have a algorithm, then we want to run this algorithm in a parameter space. But if you want to analyze this algorithm, you have to go to the feasible sets. So that's why we have to consider the relation between the parameter space and the feasible sets. So again, we have seen that if you just look at the question, original question, then you can have the critical points. But once you parameterize this question, then you have the KKT point. Then how they are related? This map phi NR, which is defined, is a bridge between the critical point and the KKT points. And actually, you can show that this map is local diffeomorphism. So this means that locally the two spaces are the same, meaning our parameterization is locally the same as our feasible sets. It's globally they are not the same, but locally they are. So using this bridge, we can connect the critical point and the KKT point. So remember that what we are interested in is this critical point. But since now we want to design our algorithm in the parameter space, we have to consider the KKT point. And this phi NR connects the two seemingly different notions, but it turns out that they are actually the same. Okay. Now it comes to the geometry part. First of all, this PSNR, as we defined before, this is a set of tensors whose rank is less than or equal to R, but it has a S partially orthogonality here. So this is a feasible domain of our original problem, right? And we can prove that this set is actually a irreducible real algebraic variety. Well, if you recall that at the beginning of this talk, if I remove this orthogonality constraints here, if I just require the rank of B to be less than or equal to R, then the set is not necessarily closed, right? If you remember that. But now if we add this orthogonality, then it becomes a real algebraic variety. We can prove that. So a very important implication for that is LRPOTA has a solution. So if this PSNR is not closed, then you may have no solution on this set for your optimization problem. But now, since it's closed, the existence of a solution is guaranteed. Okay, so that in this way we can replace this inf in our original optimization problem by just a min. Okay, and in particular, if you take S to be 3, that means if you just require B to be orthogonal, each of its factors to be orthogonal, then it is proven that this P3NR is irreducible real algebra variety in 2017. But our results generalize this to any for any value of S. And and also this PSNR, unfortunately, this domain is not smooth, because if we take this QSNR, that's just a subset of PSNR, such that each factor matrix X, Y, Z has a full rank. And also we can consider this RSNR, that's even smaller sets where you want to make sure that the coefficients sigma j are non-zero. Then you can have this sequence of inclusions. RS is contained in QS, which is contained in PSNR. And we can prove that the smooth locus of this PSNR is just this RSNR. Okay. So why we are caring about this property? Because once you can determine the smooth part, then the implication of this result is that if your KKT point lies inside this RSNR, then since this RSNR is a smooth part of this PSNR, then our question becomes the distance from a point to a manifold, right? And that means if your A is a generic tensor, then this function, this distance squared the distance function is a Morse function, meaning its critical points are all non-degenerates. Its Hessians are non-degenerates. Okay, so this property is very useful in the convergence of our in the convergence analysis of our algorithm. So but later we will see how to remove this assumption if KKT lies in RSNR. Actually, we can prove that indeed KKT always lies in RSNR. That's our next property. So here it is. So this is just for your convenience, I just record the definition of PS and QS and also RS. And what we can prove is that actually RS is a dense open subset in PS and R. And then for us, for the convergence analysis, the most important implication of this result is that RS contains almost all points in PS and R. Okay, so here I just draw the picture to show you what I mean. So this large eclipse is our PSNR, and this RSNR is almost all the PSNR, but you have some other points of which is not in RSNR. But it turns out that at the end of the day, we can ignore those points which are not inside RSNR. So the question becomes optimization on a manifold rather than just a variety with singularity. We don't want to, when we are dealing with the optimization problem, we don't want to deal with the singularity. So that's why we want to go from the variety to smooth manifolds. Okay. All right. Lastly, as I promised, that we will remove the assumption that if the KKT points lies in the RSNR. So here it is. So we can show that all KKT points of LRPOTA, sorry, there's a missing P here. All points of LRPOTA must lie in QSNR for a generic A. So if you recall the relation between QSNR and the RSNR, so if you look at here, this QSNR is just a disjoint union of those RS, say NP for smaller t. So actually what you proved is that all the KKT points lie in some RSNR. Okay, so meaning you can always treat your question as a projection problem from a point in the Euclidean space to some submanifold inside this Euclidean space. So a very important implication of this fact is that we can prove that LRPOTA has only finitely many KKT points for a generic A. Okay, so this genericity of A again guarantees that our distance squared distance function is a Morse function, and then the property of PSNR, if you recall the first fact that PSNR is algebraic variety, using these properties we can prove that the KKT points are finite. So this is a key ingredient for our linear convergence and convergence results. All right, so this is a last slide for this talk. Let me just summarize what we have. First of all, we have a tensor space versus the parameter space, and the tensor space is just our feasible set for the original optimization problem, and the parameter space is where we design our algorithm. And the issue we want to deal with is the critical point versus the KKT points, and we can show that they are basically the same. And our algorithm is a combination of the commonly used APD, alternating polar decomposition methods, and we add some proximal and truncation substeps together with the alternating least square step for non-orthogonality factors. So that's our new algorithm, IAPD ALS, for this problem. And then the good part is that this algorithm is easily implementable by numerical linear algebra, because it just involves the polar decomposition, truncation, proximal steps, and also ALS, alternating least square, is easily solved by numerical linear algebra. So all these steps are easy from the point of numerical linear algebra. So the hard part in this work is to analyze the convergence properties of this algorithm. So here's what we used in this analysis. We used some simple properties of Morse function. We proved that the feasible domain is actually algebraically is closed as a variety. And we have a stratification structure for our QSNR as a disjoint union of some smooth parts. And the first three properties are used to guarantee that we have some knowledge about the KKT points of our question. But if you want to really analyze the convergence rate, you have to use the well-known Lojacevich inequality, but we don't have time for that. But this is really a very important and commonly used inequality when you analyze the convergence rates of algorithm. Of course, in this talk, I just take D equals 3 and N1, N2, and 3 are all the same, but actually our arguments and our results are working for a general N1 through ND, anything. So actually it works for all tensors. Okay, I will stop here.
Okay, thank you. Let's have the speaker. And we are a bit over time, so if there is any quick questions, let's do it. Otherwise, we should see to the next talk. So, any questions? I have a very brief one. So, this is a theoretical work, basically, but tensors have been used in, with real data, for instance, in medical imaging. The model. So have you considered, did you try to apply it? Have you the chance of doing that?
Yeah, not yet, but actually I just want to emphasize that the reason that we consider such a question is actually people in the applied areas already using this model for several different questions. So that's why we want to consider this question, and we want to analyze the convergence behavior of this algorithm.
I understand.
Yeah. But for ourselves, we did not apply this algorithm to anything. Yeah.
So yeah, let's hope somebody will pick up this.
Yeah.
It will be interesting. Thank you
Thank you.
so much again.